Hello, welcome everyone. I'm Tyler Dare from Penn State. My co-chair for this session is Andrew Bernard from Michigan Tech. This is the first of two sessions, you might have been able to tell from the paper titles, that constitute a longer tutorial on sound level meters. This is a collaborative effort among 5 different sets of authors to try to make a cohesive group of presentations on sound level meters. We tried not to have too much duplicated information among the different papers. So you can use to ask questions, you can use the Q&A during the presentations. We'll try to answer questions after each presentation. One thing to note is there's 3 presentations in this session instead of 4, so we don't have a last paper, but there will be time for maybe a broader Q&A at the end of the session. So we can go ahead and get started on the first paper, and it's from Jim Weir.
Hello, my name is Jim Weir, and this is the first of a series of papers tasked with providing a tutorial for the measurement of sound levels. As an introduction, we will discuss the physical properties of sound and some of the key parameters for assessing sound level. In the context of this paper, I'll touch on many of the parameters, but I'll leave it to the other contributions in this group of papers to expound upon. A little about me. I've been working for Brüel Kjær for some 37 years. I'm currently the manager of our inside sales team, along with a history of application and product management with the company. And if you need to get hold of me, don't hesitate to contact me at the email address on the slide here. Okay, let's get on with it. Sound is such a common part of our everyday life that we rarely appreciate all of its functions. It provides enjoyable experiences such as listening to music or the singing of birds. It enables spoken communication, and it can alert or warn us, for example, with the ringing of a telephone or a wailing siren. Sound also permits us to make quality evaluations and diagnoses. The chattering of valves in a car, the squeaking wheel, or a heart murmur. The human perception of sound begins before we are born, and it is the second of our senses after touch to begin being processed by our developing brains. Relative to vision, which has about 1 million nerve fibers per eye, the ear has relatively few, about 15,000 hair cells in each of the cochleas. Amazingly, human hearing covers the range of 3 decades of frequency span, where the eye only spans a 2-to-1 frequency range for sensing electromagnetic radiation. The majority of the sound processing that humans perform is done in the brain. The brain looks for patterns in the firing of auditory nerves and directs us to react in reflex, triggered on frequency, content, and arrival times between the ears, or in a more analytical sense, relating the sound to other observations and our memory. The whole process is called hearing, or perhaps listening. Sound itself is the physical property of pressure variations in the air. For the ear to sense the sound, those variations need to be above 20 cycles per second and below 20,000 cycles per second. We use the unit hertz to describe the frequencies of sound. For a healthy young human, the threshold of hearing ranges from an RMS value of about 15 micropascals at 3.5 kilohertz to about 50 millipascals at the low frequency of 20 hertz. Increasing the pressure to an average of about 1 pascal is getting pretty loud. And at 50 pascals, we will be covering our ears. This wide range of amplitude response is over a 1,000,000-to-1 ratio. In acoustics, it is common to use a logarithmic power ratio to specify the sound levels. We call it the decibel. 20 micropascals is about the threshold of human hearing at 1,000 hertz. The range of human hearing is from about 0 dB to 140 dB. Sustained or repetitive levels over 135 dB peak over 115 dB RMS will cause hearing damage. The recommended average limits for an 8-hour workday is just 85 decibels. The decibel is 1/10 of a bell, a unit named for Alexander Graham Bell. The decibel is a logarithmic ratio of power. For measurement, the reference level is 20 micropascals. There are 3 common ways to create the pressure variations that make sound: vibration, flow, and explosion. Each of these has its own properties that can be used to diagnose, either by the brain or measurement instrumentation, the sources of the sound. Those properties have temporal, time-based, or tonal, frequency-based signal characteristics. Creating sound can be the goal of an apparatus, such as a loudspeaker, musical instrument, or human voice. Most often, the sound produced by a device is the byproduct of the forces or processes used in that device. In these cases, the unwanted sound is called noise. Commonly, an alternative name for a sound level meter is noise meter. The sound level meter is a tool that makes no aspirations to try to hear. Instead, it is a tool to assess the various standardized parameters of sound pressure variations in air. In doing so, with a qualified and calibrated instrument, the levels provided are governed within a certain tolerance, or more precisely, a precision. This precision and test methods are specified in the IEC standard 61672. Each certified sound level meter must make available the published results of their IEC 61672-1 testing. At a bare minimum, a sound level meter needs to calculate the RMS decibel sound pressure level with a specified temporal, fast or slow, averaging, and a frequency weighting filter of A. The A-weighted filter approximately follows the inverse of the 60 Fon equal loudness contour provided in ISO 226. The output of a microphone with a flat response and using the A-weighted filter on the signal allows the sound pressure level to measure somewhat like a human perceives the sound level. 60 dBA is approximately the level of normal human speech at 1 meter's distance. An IEC 61672 Class 1 certified sound meter, Class 2 meters are allowed to be less precise, should also include a C-weighted filter and optionally a Z or unweighted filter. The C-weighted filter is essentially flat with high pass and low pass filters at the frequency extremes of human hearing. This measurement should be relatively consistent between sound level meters. Sometimes an intermediate B-weighted filter is also specified. The unfiltered Z-weighted measurement will extend the measurement to the frequency extremes of the instrumentation and represents the best value for the level of sound pressure at the microphone. The Z-weighted response will vary from sound level meter to sound level meter based upon the microphone and signal processing limitations of the instrument. Virtually all sound level meters use a condenser microphone from a nominal 1/4 inch to 1/2 inch diameter. These diameters allow measurements up to and beyond the 20 kilohertz frequency limits of human hearing. The condenser microphone covers a wide amplitude range with noise floors, including associated electronics, approaching the lower limits of human hearing and extending above the 140 dB threshold of pain peak pressure. Specifications from instrument to instrument do vary, as does the high frequency tuning of the microphone to optimize the response from free field to diffuse field, maximally flat response. The microphone attached to the sound level meter is generally omnidirectional, until the frequency rises so that the wavelengths of the sound starts being significant relative to the dimensions of the sound meter. The electrical signal from the microphone is typically range adjusted and digitally sampled in modern instrumentation. Shown here are the directional polar plots of the Brüel Kjær type 2245 sound meter along with the diffuse field frequency response with the windscreen against the IEC 61672 Class 1 tolerances. The instrumentation sampling rate and frequency weighting filter determine the response time of the instrument. The positive or negative maximum swings of the stored signal determine the peak level. The eardrum responds to peak pressures, and this parameter is also assessed for hearing conservation. However, the human signal processor, our auditory nerves and brain, are a little too slow to respond and perceive those peak signals. The sound level meter assesses the level of the sound using an RMS root mean squared algorithm. The RMS level is proportional to the energy content of the signal. The RMS algorithm in sound level meters is specified by the standard to have an exponential averaging time of fast or slow. The names go back to the fast weighting corresponds closely to the apparent perceived loudness of the signal with an averaging time of 1/4 second. It takes 1/4 of a second for the signal to respond to within 97% of its true amplitude. The IEEE standard VU meter used in recording electronics uses a similar 300 millisecond averaging time to get to 99% of its true amplitude. The electrical time constant of the fast setting is specified as 125 milliseconds. That's half of the averaging time. It is a specification related to the design of an analog circuit that would perform this averaging. Common parameters we assess are fast maximum, fast minimum. Because the A-weighted fast response corresponds somewhat to the perceived loudness, we also compile or sample the measured level and create a statistical representation of the sound level over the measurement time. In the sound level meter, these are listed as the generic parameter L sub n, where n is the percentage of the time exceeded. For example, a parameter of LAF90 provides a value of the fast averager that was exceeded 90% of the measurement time. This value is often used as an estimate of the background noise levels. The slow RMS average is 8 times longer than the fast setting. It takes 2 seconds for the slow response to reach 97% of its pressure accuracy. When the fast level is fluctuating greatly, say more than 5 dB, you can switch to slow to get a better idea of the average of the fluctuating level. The slow weighting shows up now and then in ordinances and other specifications. As with fast, the typical slow response parameters are slow maximum and slow minimum. Because slow is not proportional to the human perception of loudness, you do not often see slow-based statistics. Note that with a steady signal longer than a couple seconds, as with a calibration tone, the fast and the slow values will be identical. With signals that fluctuate, the fast response will have a wider max-min spread than with the slow response. What if we were monitoring highway traffic noise? The signal is not steady, and the frequency of events vary with time. The average speed of the vehicles and even the mix of type of vehicle will affect the sound level. It might not be that interesting to look at the maximum level, LAF max, as that has little impact on the overall noise exposure to the surrounding areas. Instead, we want a long-term average of the noise level, perhaps 15-minute intervals. Here we'll use the integrating functionality of the meter, where we assess and update the RMS value instantly with time. This parameter is called the equivalent level. That is, the value that contains the same amount of acoustic energy of a steady signal operating over the same length of time. Note that because of the logarithmic nature of the decibel, you cannot use an arithmetic average. A minute at 70 decibels followed by a minute at 60 decibels is not 65 dB, but instead is 67.4 dB. In fact, a minute at 70 dB and a minute at only 40 dB is still 67 dB for the total 2-minute period of acoustic energy. The LEQ is the go-to measurement for most assessments of sound level. For product noise or environmental noise, LEQ gives you that physical quantity of sound exposure. The LEQ of the measurement is usually expressed as LEQ over the measurement period of time in reports. And again, we'll report it as A-weighted with the A-weighted value on the report. Sound level meters that perform this average are called integrating sound level meters. Note that we no longer need to specify the RMS exponential weighting, fast or slow. The LEQ is a linear average. Every moment of the signal is considered equally in the calculation. If the time of the measurement is not specified in the measurement requirements, it is easy to look at the LEQ value as it updates to see where it does not seem to change significantly with increasing time. Some sound level meters use a parameter called standard deviation for the LEQ that help you gain an understanding of the variation to the relative measurement time. Sound level meters with LEQ capability are called integrating sound level meters. Well, it's time to wrap up. Sound level meters are the go-to tool for assessing sound level. You want to use IEC 61672 certified sound level meters for all of your measurements. And there's a bunch of them out there. And hopefully this presentation has been helpful to you to understand a little bit more about what a sound level meter is.
That's great. Thanks a lot, Jim. That was a good introduction to the different metrics. And I think a lot of people get kind of overwhelmed by all the different settings on these meters. If anybody has questions, you can type them into the Q&A. Maybe I'll just give Jim a little maybe softball question. What's the difference between a peak level and a maximum level? Because they sound like they're the same to me.
Yeah, that's always a good common thing, because people won't know. You'll see noise ordinances written the wrong way sometimes. So when we talk about peak, we're talking about that instantaneous pressure. I described that a little bit in one of those slides. That's for instance, how far the pressure is moving your eardrum in, and that is related to the physical property of pressure. When we talk about measuring sound, though, for human use, as I said, the brain doesn't respond to that. And so when we talk about max levels, we're talking about the max energy that's coming into the ear at a time. And usually that'll be fast max for, determining how the loudest portion of a sound signal appears or limits us. A community noise ordinance, for instance, are almost always based upon fast max. Sound can't exceed this level for, during a duration of time, or this far away from a nightclub or something like that.
All right. Thanks. I don't know.
There's one more question up there. Just showed up.
Okay. So we have a question. Which of peak versus max would you recommend for like a backup alarm?
Yes, so that would be certainly the RMS value. The max level fast would be the one you would want to use for the backup alarm, because it's a transient signal. Slow wouldn't be fast enough, and fast is just right.
All right. And then we're getting a lot of stuff coming in, and we're running out of time a little bit. Brian is asking, why doesn't his 94 dB calibrator produce 94 dB on his sound level meter?
It could be that the sound level meter is out of calibration, or it could be that the calibrator is out of calibration, or if he's using a calibrator that does not have output at 1000 hertz, where all the weighting filters are the same. For instance, if it was 250 hertz, it might be 8.6 dB too low. If it's that number, then you are probably using a 250 hertz calibrator.
All right. I think we may have to move on to the next presentation, but thank you. Thanks a lot, Jim.
Yeah, and also remember, I think we're all going to stay on for Q&A at the end of the last session, this group, the third session, so that if there are more questions, we can all hang on and answer them at that time.
Great.
Perfect.